In today's lecture, we're going over how to determine the Bode plot given the transfer function. So to our left, we see that the transfer function is given. And what's really important to note is we must be really good with the log rules. And here are just some important little tables and equations I wrote down. So what I'm outlining in blue right now, let's give that a big fat outlining. We see this is the general form of the transfer function. It has to be 1 plus jw over w naught, or whatever you want to call that. That has to be the form in the numerator and the denominator. And there are some cases if it's only one part, so say it's only jw, that will mean that there's a zero or a pole, depending on where that is in the equation, at the origin. So here we see that the second thing that I wrote, I'll outline this in green. This equation is going to be the gain. Now, how do we find the gain? It's simply just the magnitude. Now, remember, the magnitude is each component squared, the sum of that, all under a square root. And finally, we have this table. I'll outline that in red. When W is less than the frequency, the component 1 plus w over wx squared all under square root will be approximately equal to 1. But if w is greater than that frequency, then it's going to be equivalent to w over w1. Why is that? Because we can simply assume that w over wx, when wx is much larger than w, or it's slightly larger, it'll be closer to 0, because when you square a decimal, it becomes smaller. And when w is greater than wx, we can simply write that as w over w1, because the 1 won't really mean anything when w is greater than wx. So the first step that we always want to do in these type of questions is we need to simplify the transfer function. So what we need to do here, remember that the table I showed earlier, or one of the equations, was the first number in the bracket always has to be a 1. So let's factor out each of these equations. We see that the numerator, it's a 5. So we're going to factor out a 5. So we'll be left with 5, 1 plus jw. In the denominator, we see the first one is already in that form, so we can just leave it. In the second one, we need to factor out a 19. Let's put the 19 out in front here. 1 plus jw over 19. So now we have everything in our form. We can simplify this further. Let's make this actually look neater first. Over 3, 1 plus jw over 19. Okay, so now that we have this, we need to determine our zeros and our poles. Now, what each zero and pole means is going to dictate where the breakthrough points are on our graph. So whatever we have in the numerator, we're going to call that a 0. Now, how do we determine what the frequencies are? Well, we see it's always going to be in the complex part of the bracket, it's always going to be the denominator. So say you have, this was 1 plus jw 0.2. If we have it in this form, we have to change it to 1 plus jw over 5, because 0.2 is equivalent to 1 over 5. We always look at what is in the denominator of the complex number part. So in this case, now for the zeros, it's always going to be the frequencies in the numerator. So in this case, we have one at w equals 5. And now for the poles, well, we're going to have 2 because we have 2 in the denominator. Now the poles are always gained from the denominator. Same thing as the zeros, we're going to look at the complex part of the bracket, and we're going to look at the numerator of that, or the denominator. So in the first bracket, we have, in the denominator of the complex part, we have jw over 3, so w is going to be equal to 3. And then our second one, w will be equal to 19. Now that we're given all the frequencies, or that we found them, we can start determining what each part of the graph will look like. So for the first part, we know it's going to be between 0 and 3. So what we have to do is we have to determine what the transfer function is going to look like when the frequency is less than 3. So using the table to the left, we see that the frequency is going to be less than each one of our corners, which is 3, 5, and 19. So that means we can simplify each of the complex roots just to be equal to 1. So what we can simply do here, we can see that right here, this will be equal to 1. This we can approximate as 1, and this we can also approximate as 1. So our transfer function ends up just becoming 5 over 19. Now, what's important to note is that the axis is in terms of a logarithmic scale multiplied by 20. So we have to take each of our transfer functions, put it under a log, and multiply by 20. So our function will simply look like this: 20 log 5 over 19. Circle that. That's going to be really important for later. And now for our next line segment, we see that the frequency is going to be between 3 and 5. So here we can write 3 is in between, or W is in between 3 and 5. So again, we've put our transfer function here. We have to find what the transfer function turns into. So here we see that the frequency is larger than 3 now, but it's still smaller than 5 and 19. So we can still write this as equal to 1, this part as equal to 1, but here, referring to table 1, we see it's different. We have to write this as W over 3. Why? Because W is now greater than 3, so it'll be a decimal number that gets squared, and when you add that to 1, it doesn't really make much of a difference, and then you square root that again. So it's just going to be approximately equal to W over 3. So what we end up with is 5 over 19 multiplied by 1 over W over 3. So to simplify this, we can write this as 5 over 19 times 3 over W, which gives us 15 over 19W. So using, again, we always have to put it under a log and multiply by 20. So using our log rules, we can simplify this into 20 log 15 minus 20 log 19 over 4. Sorry about that. We actually have to simplify this into 20 log 15 minus 20 log 19W. Simplifying this again, we get 20 log 15 minus 20 log 19 minus 20 log W. So this is what our function's going to be in terms of the gain. So now we have to find the next line segment, and that's going to be when W is between 5 and 19. So simply what we have to do again is we have to find what the gain will look like. So now that W is greater than 5 and 3, but still less than 19, we can simplify the function just like this. So right here, this will become W over 3. Because W is greater than 3, this will become 1, approximately, and this will approximate to W over 5. So what can we write our new transfer function as when W is between 5 and 19? It'll simply be 5 over 19 W over 5, or multiplied by W over 5, divided by W over 3. So we can simplify this again, the W's cancel out, and we'll be left with 5 over 19 multiplied by 3 over 5. So here we can simply just take the logarithmic value of that multiplied by 20. So we get 20 log 15 over 5, or my bad. we can take the log of that. 20 log 3 over 19. And now for the final line segment, it'll be when w is greater than 19. So now that w is greater than each one of our frequencies, we have to approximate everything as w over the frequency. So what we'll do here, we'll put in our transfer function. So this will simplify to w over 5. This will simplify to w over 3. And this will simplify to w over 19. So our new gain will be equal to 5 over 19 w over 5 divided by w over 3 multiplied by w over 19. Simplifying this further, we get 5 over 19 multiplied by 57 over 5w. So now we can simply just simplify this and by crossing out the 5s, so we'll get 20 log 57 over 19w. And to simplify this further, 20 log 57 divided by 19 is 3, so 3 over w. And we can rewrite this as 20 log 3 minus 20 log w. So now we have all of our transfer functions and what their logarithmic value will be in these line segments. So we can start actually graphing now. Found all of our functions, we can start graphing it. So how are we going to graph this just from the functions? Well, we can find out what our slopes are going to be and where the breakthrough points will be. So how do we find the slope? Well, the slope is always going to be the coefficient of whatever is in front of log w. So in this case, we see in our transfer functions, we have 2. I'll label them 1 and 2. We see that they're both negative 20. So that means we're going to have 2 slopes of negative 20 in our graph. And now how do we find... Now what about the ones without the log w? That means that's just a slope of 0. So for the first part, what we can do, since this is just a number, we can simply plug that into our calculator and find the value. When we do that, it's negative 11.59. So here, we know that the graph's going to start at negative 11.59. It will have a slope of 0 from 0 to 3. So we can simply just draw this as a straight horizontal line till 3. So our next segment, let's actually erase these, the 1 and the 2. So for this segment, we see that there is a slope. It's of negative 20, but we want to find where this will end. So we simply, into here, we plug 5 into w, and we'll find that it ends at negative 16.03. So let's have another one here at negative 16.03. So what we do, from 3 to 5, we know that it'll end at 5, and where the gain will be equal to negative 16.03. So we'll draw a straight line, and we know that the slope's going to be negative 20. Because that's our coefficient of the log w, we'll label the slope here negative 20 decibels per decade. And now we see for the second part, there is no slope because there's no log w, it's just a value. Oops. So we can simply enter in a straight line from 5 all the way to 16, or all the way to 19, sorry about that. And now for the last part, we see we again have a negative slope, and it's just going to be negative 20 all the way till infinity because there's no other line segments. This is our final one. There's no other breakthrough points. So let's just simply enter in a, oops, sorry about that. Still a little new to this, but, and we'll indicate that it goes on till infinity with an arrow. And we know that the slope's going to be negative 20 decibels per decade. So this is how we determine the Bode plot of a transfer function. Thank you so much for watching, and I hope you guys all learned something.